So in the previous section, we discussed how to create a voltaic cell that would generate electricity, and then that electricity can be used to do work. Now, the next part of this is we have to figure out how much work, or in other words, how some way to quantify the amount of electricity or the amount of work that this electricity can do. Because right now, all we have is a light bulb. Maybe we can say when the light bulb is brighter, there's more work that's done. When the light bulb is not so bright, it's less amount of work. But there has to be sort of a way to quantify this number, right? And so this is where we get into the concept of cell potential, or it's also given the symbol E cell. So this is a number that we're trying to use to figure out how much can this moving electrons do in terms of work, okay? How do we quantify this? Now, an easy way to do this is just to attach something called a voltmeter in between the two electrodes, right, to generate this work. So for example, in the zinc and copper electrode, instead of putting a light bulb there, we can just change it to a voltmeter and then see a number that comes up. Now, what I have to explain a little bit here is what is a voltmeter? What is something that measures voltage here? So before we can do that, we need to sort of think about this whole idea of a cell potential first, okay? A cell potential is basically a measure of the likelihood of the electron to flow from one side to the other. We know that when we combine the zinc and the copper electrode, that electrons will flow out from the zinc side towards the copper side, right? So electrons will spontaneously flow in this case. So then what we can say is that if we're comparing the ability of electrons to flow out of zinc versus out of copper, that it's more likely for electrons to flow out of zinc than from copper. So we can say that zinc is more readily oxidized compared to copper. Again, so we're comparing the specific elements, right? How likely is one to oxidize compared to the other one? Zinc is more likely because we see it happen. Alternatively, copper 2 plus is better at accepting that electron compared to zinc 2 plus because the spontaneous flow is from zinc, the electrons flowing out, into copper 2 plus. So the copper 2 plus is accepting that electron. So therefore, what I can say is that the copper 2 plus is a better electron acceptor than zinc 2 plus. And of course, that's another way of saying copper 2 plus is more easily reduced compared to zinc 2 plus, okay? We can also put this in terms of those reducing oxidizing agents we talked about before. So if zinc is more easily oxidized than copper, that means zinc is a stronger reducing agent than copper. And if copper 2 plus is more easily reduced than zinc 2 plus, then copper 2 plus is a stronger oxidizing agent than zinc 2 plus, okay? So the conclusion then is zinc is a better electron donor than copper. Copper 2 plus, the ion, is a better electron acceptor than zinc 2 plus. Okay, that's sort of what we want to think about with respect to this cell potential is like who's better at giving away electron and who's better at accepting electron. This is very similar conceptually to when we talk about relative acid and base strength, except that in that context, we were talking about the ability of substances to give away protons and accept protons. Now, in this chapter in electrochemistry, we're talking about the ability of substances to give away electrons and their ability to accept electrons, okay? Just as a quick reminder of that acid-base discussion, when we have a reaction like this, let's say HA and B minus, HA being the acid, B minus is the base, forming the HB, the conjugate acid, and the A minus, what we say is that if HA is a stronger acid than HB, which again means that HA is better at giving away its proton than HB, then automatically we can also conclude that A minus, its conjugate base of HA, is going to be a weaker base than B minus. This is exactly the same sort of idea that I just talked to you, but with respect to electron donation. So if zinc is a better electron donor than copper, then the zinc 2 plus ion, which is, if you want to think about it in analogy to the acid base, this would be like the conjugate species, right, of zinc. So zinc 2 plus is going to be a worse electron acceptor than copper 2 plus. Okay, so just think about how similar that phrasing of the word is compared to this acid-base situation. Okay, now another way that we can think about this when we talk about this idea of a potential is really just the ability of a substance to give away electrons is better than another one. So a lot of times the analogy that's used here is in the level of water. Okay, so if I have something called a U tube, which is basically just a tube that's shaped like the letter U, and I have a separation in between them, like a stopcock that I can open or close. When I say zinc is better able at donating electron, pretty much what I'm saying is that there is more, to some extent, more electrons on this side and fewer electrons on this side. Just like if you have two sides separated where you have water with different heights. So you know that when I open the stopcock here, the water will spontaneously flow from the left side to the right side. The same thing here in this electrochemical cell. If I open the stopcock here, which means I'm connecting the circuit to let the electron flow, the electron will spontaneously flow from left to right because the zinc side has an abundance of electron that it wants to give away to the copper side. Okay, so that's the way you want to think about this idea of a potential. There's this potential difference, and one side has more than the other one, so the spontaneous flow is to the side that has fewer electrons. Okay, so this number that we're measuring when we're looking at the difference between the two sides is what we call the electrical potential, or sometimes we call it the cell potential because the whole thing is called a voltaic cell. Sometimes we call it the electromotive force because it's the force generated by the movement of electrons. So motive means movement. Or more commonly, you probably have heard of this word, we just call it the voltage of the cell. Okay, so the number that we measure here is given in the units of volts. Now, the unit of volts actually corresponds to a ratio of 2 units, which is joules per coulomb. Now, joules, of course, you know, is the unit of energy. Coulombs is actually a measure of number of electrons. Okay, so what it's saying is that how much energy per electron is this particular combination of electrodes giving us. Okay, the higher it is, the more energy the electron can do work, okay, with respect to that particular combination. So again, in the copper to zinc combination, we get a certain volts, which means we're getting a certain joules per coulomb of those electrons. Coulomb, again, is a measure of how many electrons there are in that system. I want to say again how analogous this quantity is to height when you're talking about gravitational potential energy. So again, the idea is, you know, when we're looking at potential energy, gravitational potential energy, we're measuring the difference between the height of that water and the height of this one, right? So that one, that delta height, which is again, the height is measured with respect to the zero value here at the bottom of that water, right? So that height one compared to height two is our delta H, right? And so the higher that difference is, the more energy is going to be transferred from one side to the other, right? The more one side of the water is much higher than the other side, the more energy, gravitational potential energy you're going to get. Same idea happens here in the electrochemical cell. The bigger that difference is in the potential of this side with the potential of this side, then we get that E cell. The E cell that we measure is basically the same as our delta H. Now, I know that you would want to use delta E here, and sometimes it's not really wrong to think about it that way, but the symbol we use is just called E cell, okay? Even though it's really measuring the difference between the two sides here, the potential, electromotive potential in this case, of one side versus the other side. Okay, so again, the bigger that value is, the bigger that voltage is, the more work you can get. I like to, again, use this example of a U tube filled with water. So these is two U tubes, right? One side, they're both given the same amount of water, but on the left side, the difference in height is less, is shorter, right? And then on the right side, the difference in height is higher. So in this case, we know that if there's a stopcock in the middle and we open it up, then there's a lot more energy that's going to be transferred when that water moves from right to left compared to the one here for this picture. Okay, so more energy on this one, less energy on this one. And that's basically what voltage is measuring. It's just measuring that relative difference between the two sides. In this case, we're sort of measuring the ability of electron to flow from one side to the other. Okay. Now, when we calculate the actual E cell, we're going to calculate it by taking the final destination of the electron, so the final E, right? The potential of that, the site that has the final site, which is where, if you're thinking about the water, the final site in this case is the lower site, the initial site is the higher site. So final minus initial, since electron is flowing from anode to cathode, the cathode is our final, the anode is our initial. Now we know, based on our discussion, the cathode is the site that is less negative or more positive, right? The anode is the site that is more negative because that's where the electrons is starting to flow out from. So if we think about signs, the cathode is positive relative to the anode is negative relative to the cathode. And so we have E cathode minus E anode. That means the cathode is positive minus the anode, which is negative. So then we get a positive number as our voltage. Okay, so voltage is positive. Now, this is actually super important. Super important. So I want to really highlight this, that anytime you have a spontaneous flow, your E cell, your voltage has to be positive, has to have a positive value. This is going to be really important later on when we start calculating these voltages difference for some pairing of electrodes. And then when your E cell is negative, that means the electron flow is not spontaneous. So electron doesn't want to flow from one side to the other. So that's kind of imagining water flowing from the lower side to the higher side. Never happens, right? Doesn't happen spontaneously. We're going to have to push it in order to make that happen. But the water will flow spontaneously from the higher side to the lower side. Okay? All right. So let's talk about how this thing is measured. So like I said before, you're going to use something called a voltmeter, which is basically just measuring how much that electron is flowing from one side to the other, how much energy per coulomb that electron is going to generate. So if we use our copper to zinc pairing here, again, the electrons flow out from the zinc side, right? It goes towards the copper in this case. But then if you set up to have the voltmeter right in between those flow, you're going to be able to see how much that electron is going to be able to generate in terms of voltage. So for that zinc copper pairing, it'll be 1.1 volts, okay? And so that's the specific value of cell potential that will be generated by a zinc and copper pairing.